Hello, this is Nicholas, and I am just doing a short video here because I'm going to do another one soon. And this is going to be, it's going to be a proof of the power rule. And the power rule is probably the most important rule in differentiation. It's the first rule you're going to know. And it's gonna probably prove pretty helpful. Get it? Prove? No, it's gonna prove pretty helpful for you if you decide to learn L'Hopital's rule and use limits with it. So, without further ado, I'm sure you know that the limit as h goes to 0 of f of x plus h minus f of x all over h is equal to f prime of x, the derivative of f with respect to x, but there's also another definition of the derivative, which says that the derivative is also equal to the limit as x approaches a of f of x minus f of a over x minus a. And hopefully you can see how these are the same, but basically what's happening is you're just taking the limit as 2 points approach each other of the slope formula. So if you imagine a graph, maybe this is some sort of exponential function, and let's say this is your point A, and this is your point X, then this distance here, this vertical distance, is f of a. And this vertical distance is f of x. And what you're doing is you're letting x go to a, you're letting x approach a, so in other words, this point is coming closer, this distance is coming closer. And that's the same exact thing really as what's happening here. Okay, now, what does the power rule says? It says that if you've got a function f of x is equal to x to the n, where n is an element of the reals, in other words, n is any real number, then f prime of x, in other words, the derivative with respect to x, is equal to nx to the n minus 1. So in other words, you can imagine the power hopping down and leaving one less than itself. Now, I'm going to use this alternative definition of the derivative to prove this. So, I am gonna, by the alternate definition of the derivative of x to the n is equal to the limit as x approaches a of x to the n minus a to the n over x minus a, which is equal to the limit as x approaches a. Now, I'm going to factor this x to the n minus a to the n, and you probably don't know this factorization, but it is true. I'm going to turn it into x minus a times x to the n plus 1. Plus x to the n, oh, no, I'm sorry. I knew that sounded funny. I should have wrote n minus 1. Oopsies. Oh, geez. Eraser. Yeah. Okay, now. I'm getting used to this pad here. N minus 1. Okay, now I want to switch to pen. Okay. Plus x to the n minus 2a plus x to the n minus 3a squared plus plus x squared a to the n minus 3 plus x a to the n minus 2 plus a to the n minus 1. And I wrote that out a little more than I probably should have, but that's the idea, over x minus a. Now, you can kind of convince yourself this is true if you imagine foiling this out. And what I've done there, that factorization is, at least I think, known as the difference of nths. So, this, and it's kind of a continuation of the difference of cubes, the difference of squares, difference of fourths. It's a continuation, really. And you can fill it out and see for yourself that it's true. Now, something nice happens, right? That and that go away. So, we get the limit as x approaches a of, now I'm not gonna write out all of this. Ooh, that's an a, I swear. As x approaches a of, I'm just gonna write x to the n minus 1 plus x to the n minus 2 a plus dot 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 plus a to the n minus 1. Now, that is equal to, alright, now x goes to a basically since the function is continuous, so we get a to the n minus 1 plus, now we have a to the n minus 2 times another a, which is a to the n minus 1 plus dot 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 a to the n minus 1. So what we have here is n a minus 1, or I'm sorry, n a, n we have n a to the n minus 1s. So we have n of them, so we have n a to the n minus 1. And now look at that, and look at that. Of course, we're using x and we're using a here, but I mean, it doesn't really matter what variable you use. You can use any variable you'd like. So that's kind of a neat proof. What I'm going to do now is try to, no, I don't want to say this. It's to try to show you L'Hopital's rule, which can help you with limits using that proof. So, what is L'Hopital's rule? L'Hopital's, and I think it's spelled like this. I probably am wrong though, I'm not good with spelling. So, it says that if the limit as x approaches a of f of x is equal to L, oh, I'm sorry, f of x over g of x is equal to L, then, and f of x and g of x are just functions, then the limit as x approaches a of f prime of x over g prime of x is also equal to L. If and only if direct substitution, in other words, you plug in a into those functions, direct substitution yields 0 over 0 or infinity over infinity. So basically what this rule says is that if you've got a limit of the division of two functions, and you plug in other words, you directly substitute the value that the limit is approaching, and you get an indeterminate form of 0 over 0 or infinity over infinity, then what you can do is take the derivative of the numerator and denominator, and that function will have the same limit. So it's really a pretty cool result. So let's, as an example, let's do an example. Maybe say the limit as x goes to 0 of x cubed minus 7x over x cubed. Now notice when we plug in 0, we get 0 cubed, 0 minus 7 times 0 is 0 over 0. So we get 0 over 0. So we can use L'Hopital's rule. So by L'Hopital's rule, this is equal to the limit as x goes to 0 of, now we take the derivative of this numerator, and the derivative of a difference is the difference of their derivative. So in other words, we can just take the derivative of x cubed and the derivative of 7x and just subtract the two. That should be fairly intuitive to you. So the derivative of x cubed by the power rule, which I just proved, is 3x squared. In other words, the power hops down and leaves one less than itself, 3x squared. Now the derivative of 7x, you can imagine a 1 right here. This 1 hops down, is multiplied by this 7, right? And now you have an x to the 0 here. So you have 7 times a 1, x to the 0, which is just 7. And then again, the derivative of x cubed is 3x squared. Now, you still actually get, oh, no you don't. You get, if you plug in 0, you get, what do you get? You get 0 minus, so you get negative 7 over 0. So you get negative 7 over 0, which, okay, let me break it up. Maybe this will make it a little easier. The limit as x approaches 0 of, now I'm going to put the 3x squared over each other, so that's 1. 1 minus 7 over 3x squared. Okay, now the limit as x approaches 0 of 1 is 1. And now we have a minus. And now the limit as x approaches 0 of 7 over 3x squared, that's what? That's 1, that's infinity, right? In other words, this is going to get bigger and bigger and bigger because you're dividing by something smaller and smaller and smaller. So we get that this is just, and now really this is just negative infinity plus 1, which is still negative infinity. So that's our answer. Let's try a different one. I don't really like that one turned out to be negative infinity. Let's do the limit as x goes to 0 of sine of 5x over, say, 3x. Now, if you directly substitute, you get sine of 0, which is 0, over 3 times 0, which is 0. So you get 0 over 0. So by the L'Hopital's rule, this is equal to the limit as x goes to 0 of, now, the derivative of sine of 5x is, right, the derivative of sine is cosine, and the input stays the same. But basically, what has to happen is that you have to take the derivative of this inside term as well. So the derivative of 5x, and you might just have to trust me on this that you're taking the derivative of the inside term, is 5. So, and now the derivative of 3x is 3. So, now this is going to work out nice, right? As x approaches 0, you get 5/3 times cosine of, well, 0, which is, cosine of 0 is 1, so your answer is 5/3. Pretty neat. Now, I'm going to do one more because I think it is a good one to illustrate a point. The limit as x goes to infinity of the square root of x squared plus 1 over x. No, because you haven't learned the chain rule yet. I wish I can only limit myself. Get it? So let me look at what's another one here that maybe I could. Oh, I've got one. Okay. Let's do. It's gonna be. Probably not. Oh, oopsies. I don't know why that happened. Maybe I was erasing too quick. Sorry. Okay. Okay. Now. Oh, yep. I'm still on. I forget you have to. Okay. Okay, it's working now. Sorry. Alright, so let's do the limit as x approaches 1 of x to the 1/3 minus 1 over x to the 1/4 minus 1. Now, this by direct substitution yields 0 over 0, so I'm going to take the derivative of the numerator and denominator. So we get the limit as x goes to 0 of, now the derivative of x to the 1/3 by the power rule is 1/3 x to the negative 2/3, and the derivative of negative 1 is, well, you really have a negative 1x to the 0, and you're going to put the 0 out front, so you can have times 0, which is 0. But, so, another way to think of it is, you've got line y is equal to negative 1, right? And what does the derivative tell you? It tells you the rate at which this, it tells you the slope of a line tangent to a curve. In this case, our curve isn't really a curve, it's a line. So, in other words, if you were to pick a tangent point at anywhere along this line and draw a line tangent to this line, what you're going to get is another line. And this line, since the slope of this original line, y is equal to -1, is never changing, then the slope of the tangent line will never be changing. So in other words, the derivative is 0. And that turns out to be true for any constant. The derivative of any constant is 0. Now, the derivative of the bottom is 1/4 x to the -3/4. And this works out nice, right? Because, oh, I don't know why I wrote a 0 here. This is a 1. Now we get, okay, now as x approaches 1, right, these exponents might look messy to you, but 1 to any power is still 1. So really, what this limit evaluates to is just 1/3 over 1/4, which is 4/3. It's pretty cool. Now, just kind of as a side note, what you would have had to do, and I'm going to see if I, well, I'm not going to do it for you because the video is already getting long, but what you would have normally had to do is notice that, in other words, if you didn't know L'Hopital's rule, what you would have had to do with this limit is to notice that x minus 1 factors by the difference of cubes as x to the 1/3 minus 1 times x to the 2/3 minus, plus x to the 1/3 plus 1 by the difference of cubes. And the way you can think of that is because x is really x to the 1/3 cubed, and 1 is really 1 cubed. So those are difference of 2 cubes. So what you'd have to do is you'd have to multiply by x to the 2/3 plus x to the 1/3 plus 1 over that same thing. And then you would have had to realize that this could have factored by the difference of fourths, and then you had to multiply that by 1 over 1. In other words, you'd have to multiply by this factor here for the difference of fourths. So what I'm getting at is that it would be very messy, and L'Hopital's rule can work quite nicely. Yeah, it's a very cool. I just want to do one more example. Let's see. What else do I have? Oh, I opened up too many. Okay. One without a chain rule thing. And you guys haven't really learned that yet, but I just don't want to give you that right this moment. Okay, I guess I'll do this one. So x cubed minus 3x squared plus 7. I'm gonna have to make a new one. Maybe it wasn't worth doing. So it was the limit as x approaches infinity of x cubed, or x, x squared minus 3x and I believe it was plus 7 over x cubed plus 10x minus 4 plus 7. Okay, now if you plug in infinity, hopefully you'll see that you're going to get infinity over infinity. So you can apply L'Hopital's rule. You're going to get that that's equal to the limit as x approaches infinity of 2x minus 3 over 3x squared minus 10. And then you can apply L'Hopital's rule again because you're going to get infinity over infinity. It's equal to the limit as x approaches infinity of 2 over 6x, which is infinity. Now, Yes, L'Hopital's rule works in this case, but a thing I want to point out is that notice that since you're approaching infinity, what happens really is that this 10x plus 24 and this 3x plus 7 go away. And the reason for that is because relative to x squared, 3x and 7 increase or decrease very insignificantly. Right, this 7 is just a constant. And this 3x, although it does increase, it does not increase nearly as quickly as this x squared. This x squared is what's known as the dominating term. In other words, it is the term that really controls or really dictates how quickly this numerator will increase. And the same is true for this x cubed. So really what I'm saying is that this limit here, right off the bat, you can just say that that's equal to the limit as x approaches infinity. Oh, I shouldn't have written infinity here. Right, as you approach infinity, you get 2 over a really big number, which is 0. So you get the limit as x approaches infinity of, you get x squared over x cubed, which is equal to the limit as x approaches infinity of 1 over x, which is 0. So just 2 different ways of doing it. And I think that is all. If you have, I guess I kind of want to do this. I remember Mr. Mac kind of got to, we had the limit as h goes to 0 of cosine of h, not hyperbolic cosine, minus 1 all over h. And we wanted to prove that this is 0. So what am I going to do here to prove that this is 0? I'm going to multiply by cosine of h plus 1 over cosine of h plus 1. Basically, I'm going to rationalize, well, not rationalize, but I'm going to complete the difference of squares in this numerator here. So I'm going to get the limit still as h goes to 0 of cosine squared of h minus 1 over, times, that was my cat, h times cosine h plus 1. Okay. Now I know that 1 minus cosine squared h is sine squared h, but I have this flip-flop. So basically what I'm going to do is I'm going to make this numerator into the negative of 1 minus cosine squared h, which is negative sine squared of h. So I get the limit as h goes to 0, and I can really put this negative sign up front because it's going to be a constant. It's really negative 1. So of sine, that's a sine squared of h over h cosine h plus 1. Now this is equal to the negative of the limit as h goes to 0 of, now we have sine of h over h times sine of h times 1 over cosine of h plus 1, which is equal to, now we can just directly substitute into this whole big expression here. Now this first limit, so we get, we have the negative of, and now we have this sine of h over h as h approaches 0 is 1, and we prove that, times limit as h approaches 0 of sine of h, which is just 0, times this, which is going to give you a half, which is 0. Pretty cool. And now you can use that to establish that the derivative of the sine of theta is the cosine of theta. So a way you can do that is you can say that the derivative of sine of theta is, or the derivative of sine, let's use x. The derivative of sine of x is equal to sine of x plus h minus sine of x all over h, which, if you remember your angle addition formulas, is sine x cosine h plus cosine x sine of h minus sine of x all over h. Okay, now, oopsies, this is all the limit as h goes to 0. Now, I'm gonna make this numerator into, so I can get a common factor out. I'm gonna make it sine x cosine of h minus sine of x plus cosine x sine h. That's okay, right? I've just flip-flopped those two. Now, this is going to be equal to, I should just write down here, the limit as h goes to 0 of sine of x times cosine of h minus 1, h, just put parentheses there really, plus cosine of x sine of h, and I'm just going to make it over this h here. Because really when you multiply them, it'll be over the whole thing. Okay, and also, since I split this apart basically, in other words, in other words, you have to, since I'm splitting this apart, I have to put it over h here, for each term that where you're adding. So, now, okay, the limit as h goes to 0 of sine of x times cosine h minus 1 over h. Well, we know that, we just showed that the limit as h goes to 0 of this is 0. So we get a big 0 right here. Now, we also show that the limit as h goes to 0 of sine of h over h is 1. So now we have 0 plus 1 cosine x, which is equal to cosine of x. So d over dx of sine of x is equal to cosine of x. And what this d over dx is equal to f prime of x is equal to whatever, however other way you want to write it. In other words, what we're saying is that we're taking the derivative with respect to x. That's what we mean here. Just two different ways of writing it. This is Newton's way. This is Leibniz's way. Just two different ways. Okay, I think I am kind of happy with this. Probably the main takeaway from this video is the use of L'Hopital's rule. And it works out very nicely with indeterminate forms. So that's the big takeaway here. And if you've got a limit with trig functions and you've got a sine in there, well, now you know that you're going to get a cosine when you take its derivative. Okay, I believe that wraps it up. Oh, no, it doesn't, because I have to write quod erat demonstratum QED. And we're done.